We're going to talk about traversing trees, which is the subject of now that we've constructed a tree and it's got all our stuff in a nice sorted order for us, how do we then look through the contents of the tree to get our sorted stuff out in that sorted order? So there are basically, the goal is to visit each node once and only once. And earlier today, we talked about how to search through a tree if we're trying to find one item. In this case, we're traversing the tree, which means visiting every item. And there's different ways we can visit them, and we can get different orders. But the ultimate goal is that we visit every node once. And there's actually only 3 total operations that we have on the tree. We can visit the current node, and then we can traverse to the left child, and we can traverse to the right child. So at any given point, that's basically our 3 options as we're traversing the tree. So there's 2 main, most important types of traversals. There's depth first and breadth first. And you are going to actually implement both of these as part of your maze generation project. So when Dion was talking about depth first and breadth first, this is what he was talking about. So in depth first search, the idea is basically that you go down the branches of the tree first. So you visit the node you're on, and then you go down the branches. Whereas in breadth first, you go across the levels. So on a tree, there's levels, right? The root is in level 1. If that tree, the root has 2 children, those are on level 2. So breadth first starts at the top level and then goes through the tree sort of across the levels. So these are the 2 main types. Both will show up in interviews, by the way. So you'll have to know how to do both of them, which is why you will be doing both of them as part of your generating mazes. So let's talk about depth first search first. So in depth first search, you always end up going left down the left part of the tree before you go right. And there's actually 3 subtypes of depth first search, but they're all basically the same thing, just swapping a couple lines of code. So they're very, very similar. Those 3 things are called pre-order, in-order, and post-order. So these orders only affect when we visit the node. So that's not quite clear because I haven't really defined what visit means other than we're on that node as part of our searching. In general, it might mean many things. So if you want to print out every item in your sorted binary search tree, then the visit command can be as simple as just a print statement that prints out the data in the current node. But maybe you have all this sorted data and you want to manipulate it somehow. So if you have a bunch of numbers in your binary search tree, and let's contrive an example. Let's say you just want to increment every number by 1 for some crazy reason. Visiting could just be taking the data stored in the node and incrementing it by 1. In our case, for this discussion, visiting is just going to mean printing out the node to the terminal. So let's talk about pre-order depth first search first. By the way, you'll notice that each of these, the depth first searches, are all recursive. So just like the search we did earlier today, these are recursive. Recursion as a review means that you're calling the function from within itself. So here we have pre-order depth first search. The only parameter is the node that we're currently searching on, the node that we're currently at. And it's dead simple. Basically, you first check to see if the node even exists because you could call pre-order depth first search on an empty node if a node had no child. And then if it exists, you visit it. So if it exists, we print it. And then you call pre-order depth first search on the node's left child, and then you call pre-order depth first search on the node's right child, recursively. So, given that this is the algorithm, and this is our tree with f at the root, what is the order that we are going to visit? Like, what will we print out as we visit? So, we're going to pass f, the root node, as the parameter the first time we call it. So what is the first thing we're going to print? Given this code here, f, right. So put a little number 1 above the F node to indicate that. So then what is the next thing we're going to print? B. Why B? Okay, because we're calling preorder depth first search on the left node first. And so when we call that, that means B is the parameter here, B is not none, and then we're going to visit B. Okay, cool. So what about now? So we're currently on B, we just visited it. What's next? Well, we're going to call preorder depth first search on B's left child. So now we're going to print out A. So far we've printed out F, B, A. So there's A. All right, so now it's a little bit different. What's next? D? Yeah, why? Okay. So A has no children, so it's going to call preorder depth first search on 2 none values, but basically that will just break, nothing will happen. And then we'll pop up 1 level in the recursion, so then we'll go back to when B was the node that we were currently doing this operation on. So if we remember, B called node.left first, so that's when we did A. So now we're back to B as being the parameter, and we're going to call preorder depth first search on B's right child. So we're going to print out D. Okay, what do we do next? Okay, so it should be pretty clear by now. So now we're going to do C. Then C has no children. We go back to D, print out D's right child, print out E. Now what happens? Okay, G, I, then H. So why G? Well, these are all accounted for. So we're currently on E. It's going to pop back up to D. Then there's no code after it called the D's right child. So then we're going to pop back up to B. Again, same situation. Pop back up to F. And so we'll be back to when we first called it in the recursion tree with F as the node in the parameter. So now we already got the whole left subtree of F. Now let's do the right subtree of F. We call preorder depth first search on node.right. We print out G. Then we call node.right because node.left is none. So then I, then H. Okay, so that's preorder. So the ultimate thing we get is like this, F, B, A, D, C, E, G, I, H. Well, that's not actually sorted, right? Sorted would be A, B, C, D, E, F, G, H, I. So what we have here is preorder. So visiting every node and printing it when we visit it. Let's talk about in order. The algorithm is the exact same, except for we took lines 3 and 4 and we swapped them. So, all right, what's the first thing we're going to print out in order? A. Why A? Okay, so because we're going to go left as far as we can before we even reach the first visit statement. So we pass in F as the root node. F is not none. So then we do in order depth first search of F's left child. So then B is the parameter here. Then we do in order depth first search of B's left child, and then it's A. A has no left child, so then we visit A. So there is A. So now what's going to happen? Okay, print B. We think it probably should be B because it's called in order depth first search, and we expect that B comes directly after A. But why B? Okay, A doesn't have any children, right? So we just visited A. It has no children, so in order depth first search of A's right child won't do anything. So then we pop up one part in the recursion stack. We're at B, so we just visited B's left child, which means the next line of code is to visit B. So then we'll print out B. So there's B. So now what is next and why?
C.
Yeah, why C?
Right,
okay, so we're currently on B, and next is going to be C because we're going to travel to the right, but then this right D has a left child. So before we get to even visit D, we have to go to the left child. C has no children, so we'll visit it, and so on. So the next one is going to be D because we pop up in the recursion stack and then visit D after having just visited D's left child. And then the same thing happens. We visit E, which is D's right child. Then F, G, H, I. Okay, so any questions about preorder and in-order depth first search and the difference between them? So we can see we got this completely different behavior just by swapping this line of code in the recursive call. Yes, Ignat?
Just to make sure, this is a sorted tree, right?
Yes.
Okay.
This is a sorted binary search tree. Okay. So now let's do post order. Oh, so here's our correct order. So when you want to get the ordering, like basically binary search tree is an ordered data structure, just like linked list, just like array. Although those are not necessarily sorted unless you sort them. Binary search tree is sorted by definition. If it's not sorted, then it's not actually a binary search tree, it's some other kind of tree. So to get our sorted elements out of the tree is like a pretty important function for binary search tree. So the way you do it is with an in-order depth-first search. This is how to get the stuff out of the tree in the sorted order. It is kind of like a depth-first list, but necessarily we don't have to print things, we could do other things. It's more of like a depth-first traversal, I would say, but it's called depth-first search. And you can use depth-first search to actually search for one item, in the case of the maze. And then once you find that one item, you can stop. But that's like a different thing entirely, right? In this case, we're trying to print out and visit every item. Okay, so post order. It's exactly what you thought it was going to be. We just took the visit and we moved it to the bottom. So what's the first thing we're going to print out here? Ignat says A. Why do you say A? Okay, so there's A. Sounds good. What is the second node that's visited and why? Yeah, Dennis.
C.
Okay, C. Why C? Okay, it goes back to B after we visit A.
Steps forward to D.
Okay, steps forward to D here. Yeah, D goes directly down to C. C has no children. Okay, yeah, so there's C. All right, so now what do we do next? What's the next thing that gets printed out? Yeah, Dan? E. Okay, why E? Okay, so Dan said, we're done with C, so then we return back to D. We just came from D, from going node left, so then we go node right. Node right is E. E has no children, so we visit it. And that's correct. So then now what's next? This is sort of like a little bit of a different case from those three. Okay, did you say D? Why D?
Because now in D, you visit the left, visit the right, now we visit it.
Okay, so D has visited both the left and right complete subtrees. So the only thing that's left to happen in D is to visit D, and that's correct. And then the same exact case for B, right? We've already visited the entire left and right subtrees of B, so that recursion is completely finished with. The only thing left is to print out B. Okay, so now what's next? Yeah, Dave. So Dave says H, I, G, F. Why? Right. Okay, so we're back to F. We have to go right before we can visit F. We're here. We have to go right or left. There's nothing left, so we go right. Again, have to go right or left. Left is first. We go left. H is a leaf, so we print it out. It has no children. And then we go back up the recursion stack. Then it prints I, then G, then F. Okay. Any questions on post-order depth-first search? Here. Oh, so why did it go back from H? Okay. So before that, we were on F, and we already did the entire left subtree of F. So then it was time to go right, because basically F is the parameter here. We do all of post-order depth-first search on F's left child, B. So that's completely done with. So then we do post-order depth-first search on F's right children. So that calls this function again with G. G does the same thing. It tries to go left, it can't. So then it tries to go right, it can. It goes to I. I tries to go left, it can. It has a left child. And we're on H. H calls post-order depth-first search on left and on right, both are actually none. So this condition is never true for those children, and it never visits anything. But once that's finished, we are now here. We executed these 2 lines of code, and now we're here with H, so we print it. So then, this takes us to why do we then pop back up and print I, G, and F? Well, I called post-order depth first search on H, so we just finished, we're back to I being the parameter here, and we just finished calling this line of code on I's left child. So now we have to move on to the next line of code, which is post-order depth first search on I's right child. I doesn't have a right child, so then we move on to the final line of code, we visit I. And then we pop up the stack again. So how did we even get to I? Well, first we were at G, and G called post-order depth first search on node.right. So we pop back up, and now we're back to G at the place where G called post-order depth first search on I. So that means we're on this line of code. So then we move to the next. We visit G. Oh, sorry. We visit G. And then finally we visit F, having visited both the left and right complete subtrees of F. Does that make sense? Okay. All right, so we're all good on depth first search. All you have to remember for interviews is how to do it. It's super short. You just call depth first search on the left child and on the right child, and the order of the visit determines whether it's pre-order, in order, or post-order. So pre-order means you visit first, in order means you visit after the left but before the right, post-order means you visit after both left and right. Yeah, Alan?
What's a useful application of post-order DFS? It seems so strange.
So if you notice, post-order is a little weird, but well, actually, so I was going to say we visited the leaves of the left subtree first, and then we did the internal structure of the left subtree, and then we visited the leaves of the right subtree. Past that, I'm not sure. Do you have any examples?
This is how we evaluate algebra.
Oh, right.
If all the internal nodes are operators and all the leaves are numbers, this is like how you evaluate algebraic statements or expressions in memory.
Yeah, so that's a really good point. When compilers are parsing through a bunch of tokens, like 1 plus 2 times whatever plus something, compilers are actually constructing trees like this to determine basically the algebra and the order of operations. And then you can do post-order depth first search. So a leaf would be a number, so it'd be like 1 and then plus 2, and you can calculate things that way. So that's kind of a cool application. Past that, you probably actually won't see it outside of interviews. Yes? Okay, that's cool too. So decision trees are a way to do artificial intelligence, kind of. It's more like just programming what the AI should do, and you can do it with this too. All right, so let's talk about breadth first search. So breadth first search is different. Instead of actually navigating the tree following the hierarchies, we're going to navigate level by level. So, spoiler alert, this one we're going to print out F, then B, G, then A, D, I, then C, E, H, level by level. So that's kind of cool, but then the question is, how do we possibly do that? Because our binary search tree data structure basically only allows us to go down to children, and then only through having stuff stored on the stack can we go back up to the parent. And that's kind of just part of the fact that we did it recursively. How are we possibly going to do this? Well, the standard breadth first search is not done recursively. The sort of standard vanilla one is done iteratively, and it's done using a queue. So here, I import deck, which is a built-in data structure in Python that allows you to do queue-like things. It allows you to append to the back in constant time, and pop from the back in constant time, and allows you to append to the front and pop from the front in constant time. So it's pronounced deck, it's spelled DQ, and this is the data structure we're going to use as our queue in our breadth first search. So let's look at it. What happens when we call breadth first search with the root node, which is F? Well, first we construct a queue, And then we use the queue and we append the root node. So now we have our queue and it's got one item in it, it's got root node in it. And then we have a while loop. So this is where it's iterative versus recursive, the fact that we have this while loop here. So while the length of the queue is greater than 0, we're going to do all this bunch of stuff. So that means once the queue is empty and has no more nodes in it, we're done with our breadth first search. So currently our queue is length 1. It has f in it, so this while loop holds true. So we access that node and remove it from the queue in one line of code with this here. So we pop it off the left side of the queue and assign it to the node variable. And then we visit the node. So we print out f. So now is where it's like the actual guts of the logic. If there is a left child of f, then we add it to the queue. And then if there is a right child of f, we add it to the queue. So you can see right away, we started with f, then we added b, and then we added g. And the fact that we're popping off the left side of the queue means that next we'll visit b, and then after that we'll visit g. So you can sort of reason that it looks like we're probably going to go level by level, right? We went f to b to g, and then actually once we're on b, we're going to add a and d. So let's go through a couple more steps. We're on f. Actually, we just finished with it, and now our queue has b and g in it, in that order. So now it's length 2, so the while loop still holds true. So we grab the node from the queue, from the front, which is b. So now node is b. We visit b, we print it out. And now if b has a left child, we add it to the queue. If b has a right child, we add it to the queue. So now the queue is GAD. So next we visit G, we grab it out of the queue, and we add the left child and the right children. It has no left child. We add I, the right child. And so far we've printed F, B, G, and we are visiting them in level by level order, left to right, like was the goal. So we'll kind of breeze through the rest of it. We're at A, no children, nothing happens. We're at D, we add C and E. Then we're at I, we add H. So now the only things left are C, E, and H. No children, no children, no children. And we have successfully printed out in breadth first order. So a little bit more complicated than depth first search, simply in terms of line of code, but fairly straightforward algorithm. Any questions about breadth first search? Yes? Oh, that's a cool question. So if instead of popping from the front, we append to the back and pull from the back, at that point, it's a stack instead of a queue. And what would the order be? Well, we would visit F first, add B and G, then we would visit G, add I, then we would visit I, add H, then we visit H. So we've visited F, G, I, H. Then we would visit B, then D, then E, then C, then A. So it's kind of like, it's not actually a breadth first anymore. It's not like it went level by level reversed. It's more of some kind of stack, or sorry, some kind of depth first kind of thing. It looks like a depth first search actually in which we do it post order but visit right before left. Might be the correct answer. But you'd have to check on that. Okay. So that's actually it. Any questions about those two concepts? How to traverse a tree. Remember, we're not searching, we're traversing, so we're trying to visit every node. Two main ways to do it, depth first, breadth first. You will implement both in making your mazes. Yeah, Mike?
Could you expand a little bit on the rationale behind a situation where you would traverse a tree as opposed to needing to search for what you need?
Oh, okay. So this is a good point. Basically, a tree is a data structure, but we don't actually care how it's implemented as long as we're just using it. We only care about its properties. And the properties are that it's a sorted data structure and that it has fairly fast log of n insertion deletion. So in any case, actually, where we want to keep a sorted list of data, which is many cases, including databases, like, yeah, anything where like we have a spreadsheet program and we want to be able to sort stuff, or anything at all where we just need anything sorted. The binary search tree is the way to go because of its property as being sorted. But in those cases, it being sorted is mostly only useful if you need to eventually get out the sorted list in sorted order. So you could use it entirely as like a key value map, and in fact, binary search trees back a lot of hash tables. Sorry, back a lot of dictionaries. So a lot of dictionary data structures are not actually hash tables. The Python one is, but a lot of them are binary search trees. So you can use it for random access, but they're also very useful for actually putting in a jumble of stuff and then reading out of it in a search, like a sorted order. So any case where you would need a sorted order of things, binary search trees are super useful for that.